Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. If you like this video, hit the like button and subscribe. If you have any comments or questions, leave them down below. And once again, I want to thank you for watching and hope to see you again and again. Thank you. Okay, today we're going to talk about derivatives of trig functions. We're going to start with two very important and interesting trig functions. Here's the first one. Sin x over x. The limit of sin x over x as x approaches 0 equals 1. We're going to investigate, try to analyze, then we're going to show you the proof. So if you make a table and try to get close to 0, here plus minus 0.1. The answer is 0.998334165. If you get even closer to 0 from right and left, I get even closer to 1. You see I have more 9s here. 9, 9, 9, 9, 4 9s, then starts 8. Point, of course. If you even get closer to 0 from right and left, 0.001, I get more 9s. So the values of sin x over x rounded to 10 digits, as you could see right here, appears to approach 1. Let's see it in a different view. If you try to graph sin x over x, it looks like as x approaches 0 from right, the graph is taking you up to the level of 1. As x approaches 0 from left, the graph takes you up to the same level 1. The graph of y equals sin x over x suggests that the limit is 1. Well, there's a small circle here. I don't know if you could see it, but that says that the function sin x over x is undefined at x equals 0, which is true. It's undefined. Consider the three regions with central angle x. That angle lives between 0 and pi over 2 in the first quadrant. Here's the first graph. It's a right triangle, OAD. OAD. Right triangle right here. This is a unit circle. I have enough letters, so I did not call this another letter, but we know that the radius is 1. So let's keep that in mind. Let's look at a different region. This is called a sector, part of a circle, all right? OAC. This is another right triangle, but going out of the unit circle, OBC. All right. Now, most books, they do this graph in one graph. I tried to make it separate graphs so you could see clearly the approach. And it's my style, my way of studying, my way of teaching. I believe when you see it this way, and let's say later on, if you try to remember the proof and you kind of memorize a graph like this, you will know how to start and build it. At least that's my way. I try my best to make my videos simplified math lectures with examples. And hopefully from this example or this picture, you could see my point. So let's notice the following and take a look at some notes before we start steps. First of all, we know that this area is less than this area is less than this area, referring to what those are titled, and in colors it's kind of like red and bluish and green, which is clear, right? Okay, we're gonna keep that in mind, but we have other things to consider. Because the circle in the graph is a unit circle, we have the following. O up to this point is 1. O up to this point, which is A, is also 1. O up to C is also 1. Keep that in mind. So OA is the same thing as the radius, which is OC, which is 1. One more. See this red triangle? This is called opposite, this is called adjacent, and this is called hypotenuse. So what do you think sine x is? Instead of calling it theta, they call it x. Sine x would be opposite over hypotenuse. But the hypotenuse is 1. So just the opposite. That's one benefit from the unit circle. Sine x is AD over OA, but OA is 1. So just AD, which is the opposite. So this, you could write next to it, sine x. We're going to take advantage and use the same idea to write this in terms of cosine. Cosine x is adjacent over hypotenuse, but the hypotenuse is 1, so it's just OD right here. Going to the green one, tan in this case is opposite BC over adjacent OC, but OC is the radius of the circle, which is 1. So tan x is going to be BC over 1, which is just BC. Okay, let's summarize this before we move on. Sine x, cosine x, tan x. All right. Now let me talk about the unit circle and the sector of a unit circle like this one right here in a different slide. Then I'll come back to this problem. I think you'll benefit from memorizing and why that formula is. This is a complete area. This is just a portion of the whole thing. We call it a sector. To build a proportion, I have titles right here. And this is one way to build proportions. Excuse me. Area related to corresponding angle. The bigger the angle, the bigger the angle, the area. So if you want to go all the way around, the area is, excuse me, pi r square. The corresponding angle, excuse me, is all the way around 360 degree, or we call it 2 pi. That's the yellowish area. In this case right here, the area is unknown, so I'm going to call it x. X is for the unknown, since the angle is called theta, so I'm not interfering with the name for the angle. The corresponding angle is theta. All right. Build the proportion. This to this is like this to this. And that's how we do it. Pi r squared compared to 2 pi, or 2 pi, is the same thing as x2 theta. Cross multiply. Since our focus is in x, we need 2 pi by itself. So we multiply across, and then we divide by 2 pi to leave x alone. That's kind of like 2 steps in one. Since this is not our title, I'm trying to go a little bit fast. But at least you see it, and you know what I'm talking about. So x is half, pi cancels, half r squared theta. And r is the radius. In our case, it's x, so we're going to use x. Area of a sector of a circle of radius r formed by a central angle theta is half r squared theta. Okay, let's go back to our problem. Here's our problem. We said this is less than this, less than this. But what is this? Area of this triangle, half times base times height. The base is cosine, and the height is sine. Trying not to repeat myself, as you can see, because we know what we're doing now. So it ends up half cosine sine. Area of this, which we agree on, I gave you a whole slide about what is the area of a sector, half times r squared theta. But what's r squared? R is 1. All right? And our theta in this case is called x. So it's x over 2. Okay? Half times base times height. But what's the base? The base is 1. From O to C, that's 1. And what's the height? we agreed on it as 10. Okay, so it's half 10. Now we're going to put this less than this, less than this, and move on. That's interesting. So this is my hint for everybody. To get started, to talk about sin x over x, those are the graphs to help you memorize how the proof is started. Moving on to a clean page. This is what I have. We're going to write tan x as sin x over x, over cosine x, sorry. I'm going to multiply by 2, multiply by 2, multiply by 2 to get rid of halves all over. If I do that, I'll get x by itself here. But we need to build or cook something to make us prove what we are looking for. Keep in mind what we have. If I teach on the whiteboard, I always keep it on the right side or the left side corner of the whiteboard. That this is what we want. This is what we want. Let's keep it in mind. Stay focused and keep it, which is sin x over x. We need it. So let me multiply instead of 2 by 2 over sin x. And because we are in the first quadrant, these inequalities, they're not going to flip. These are positives. All right. Why 2 over sin x? 2 is going to get rid of the halves. Sin x is going to cancel from here because that's going to be in the way. It's going to show up here, but it's going to show up the other way around. X over sin x. All right. Sin x cancels from here, shows up here. Let's flip this to make it look like ours. Take reciprocals and reverse the inequalities. We're going to reverse them. See, I use different color to highlight that. All right. Now in life, we don't say most of the time in math, greater than. We say less than. We say like 2 is less than 5 and 5 less than 7. That's how we say it. So let's reverse them the other way around. So instead of saying cosine is the smallest, sitting here, we're going to put it all the way to the left. So sin x over x is greater than, as this one says, greater than cosine x, same thing, and less than 1 over cosine x, and less than 1 over cosine x. Okay, sounds good. Let's apply the limit to each side. We could do that and we don't have to flip because we're still positive. Everything is positive. Cosine is positive, sine is positive, x is positive. We are in the first quadrant. So nothing of issues to be careful about. With inequalities, we have to be careful when there is something happening with negatives, like multiplying or dividing. Apply limit to all 3 sides. You see this guy? That's what we want. So we kind of built it, we kind of cooked it. In other words, we want it to happen. We didn't know where to get it from, but the graph that I showed you is the way we made kind of like a relation that we kind of twist things around and bring sin x over x, as we could see. What's the limit of cosine x as x approaches 0? That's going to be 1. Same thing, if this one approaches 0, 1 over 1 is going to approach 1. So this approaches 1, and this is also approaches 1. So where this is going to go to? Still 1, has to, by the squeeze theorem. We're done. I think that's good enough for this, and we have more to cover. Let's move on. Similarly, we can show that cosine x is less than sin x over x less than 1 over cosine x also holds in the 4th quadrant. Books usually skip those and ideas like that because it's kind of hard to cover in lectures or books every single aspect. If it's the same thing, they can mention it and move on, and I'm going to do the same. We're going to take another interesting one. Limit cosine x minus 1 over x. Why do we need that? Because it becomes handy when you move on and prove things. Those basic ones, major ones, you use them and move on. So let's work on this one. We're going to take it to the side and start work on it. How do I approach this? In a different way. Doesn't have to be graphs. See this right here, cosine x minus 1? To me, it's like a minus b. Do you remember something called a minus b times a plus b equals a square minus b square? That's difference between two squares. So we're going to take advantage of that. I call them skills, as I always do. I bring the a plus b, and now this is a square minus b square. But why cosine square minus 1 equals minus sine square? That's another fact, another trig identity that says sine square plus cosine square equals 1. If you want this right here, I could move the 1 here, that becomes minus 1, and move the sine square to the other side, becomes minus sine square. That's like 2 steps in 1. So that's how we got it from here to here. All right, I'm going to take one of the sine x's out. I'm going to take this x out to the front and apply the limit. The limit of the product is the product of the limits. Those are basic limits rules that you need to be familiar with. We did this because we're building, as you could see, as we move on. We proved this so we could use it anytime we want now. And what stays inside, minus sine x over cosine x plus 1. Some books, they put the minus right here. I kind of prefer to see it up there because it's so clear here that there is a minus. But sometimes when it's like aligned with the fraction, it's kind of hard to see it, or it's easier to miss. So it's just an idea. All right, let's move on and see what's going to happen. Here we have sine x and we have minus. So the minus is not an issue. I could pull it outside. As you can see, I could take it outside. What is the limit of sine x as x approaches 0? It's 0 because sine x graphically starts from the origin. If you remember, that's kind of like to help you out. Limit of cosine x, which is this part here, and it starts on top at 1, so it's going to be 1. So this goes to 0, this goes to 1, and this is 1, so it's going to be like 0 over 1 plus 1, which is like 0 over 2. And we know this, which is 1, right? So 1 times 0 over 2, which is 0, as needed. Okay, we're done with the two major trig functions as derivatives. Those are derivatives. The limit is derivative. Let's take an interesting example. Sine 3x over x, limit as x approaches 0. I know the answer because I have experience and I know what I'm doing. The answer is going to be 3. Well, let me show you how. I'm going to multiply by 3, multiply by 3. As you can see, I have different colors to show you that I came up with the 3's. That's like multiplying by 1. When you multiply by 3 over 3, it's like you're multiplying by 1 and everything's fine. This 3 in my way, I'm going to take it to the front. See it? Now, let's take advantage of what we know about sine x over x, but this one doesn't look like exactly sine x over x, but we could make it look like it. Here we go. Let 3x be called t. As x approaches 0, 3x approaches 0. It even approaches 0 faster. So as x approaches 0, 3x that I'm going to be calling t approaches 0. So to make the story short, if x approaches 0, t approaches 0, so I'm going to change this to t approaches 0. 3x will be called t, 3x will be called t. Now looks clean. Doesn't have always to be called x. Could be called t, could be called u, anything. So this is 3 times 1, which is 3, as I told you, right? Let's take a different one, slightly different, but same topic. Sine 3x over sine 4x. I'm not going to give you the answer now, so just be with me and I'll show you how. Well, earlier they gave me an x and I was missing the 3. Here I'm missing an x, right? And I'm missing an x here. No problem. Let's bring it. I'm going to divide the numerator. I'm going to divide the denominator by x. I could do that because x is not 0. we are approaching 0, we are not equal to 0. That's why we could do that. I'm going to multiply top and bottom side here on the numerator by 3. I'm going to multiply the denominator, top and bottom side, by 4. See the colors? Just like the previous example. I'm going to call this one T. I'm going to call this one U. Same process. Pull the 3 out, pull the 4 out. The limit here is 1, the limit here is 1. So the answer is 3 out of 4. So when you see this later on as a multiple choice, what's the answer? 3 over 4. Okay, let's talk about a theorem that is important. The derivative of sine x equals cosine x. Proof. How we could do that? This time we're going to use the formula. The definition of the derivative. We're going to start with it. Now f of x is defined to be sine x. I'm going to rewrite f of x as sine x. Instead of writing f of x plus h, I'm going to write sine x plus h because my function is the sine function. All right. Do you remember the sum identity for sine? The sum identity, sine addition identity is sine x plus h equals sine cosine plus cosine sine. And you alternate the angles. So we're going to apply this right here. This is at the end, so it's going to show up at the end. You see that? So this right here is replacing sine x plus h, and you should know where I got that from. All right, see this sine x? See the sine x? I'm going to take it out as a common factor. From the last factor, I'm going to stay with minus 1. Factor out sine x, and we'll have a minus 1 from the last factor. From this factor, I'll have cosine h inside. This stays out by itself, right there by itself. All right, now we're gonna split this fraction into 2 parts. You see the plus sign? That's my plus sign. This divide by that, and this divide by h right here, and apply the limit to both. The limit of the sum is the sum of the limits, and that's what I have. Next, sine x and cosine x don't talk to the limit as h approaches 0. There is nothing. Sine x and cosine x are independent of h, so I could pull them out. To me, it's like they're constants. I know x changes, but we are worried about h approaches 0. So cosine x has nothing to deal with h approaching 0. Same thing here. So we take them out. Take this out. Take this out. Have you seen this? Have you seen this? That's interesting, right? See why we started with those? If you don't have them, we're stuck, right? Well, what's interesting about math is everything goes smoothly if you know everything on the right time, the right place, and it builds on and on. Those are now facts for us. So that's a 1, and that's a 0. Sine x times 0 plus cosine x times 1, and the answer is cosine x. Do it the other way around. We're gonna skip. As I said, we can't do everything. We can show that the derivative of cosine x equals minus sine x. I'm saying it clearly, and I'm using different color to show you that the derivative of sine is cosine, but the derivative of cosine is not sine, it's minus sine. In the same process, you could show that. Okay, what's the derivative of tan? Secant square. Let's see how we're going to start. We're going to start by building or rewriting tan as sine over cosine. Sine over cosine. I'm going to use the quotient rule. You know how to do it, right? G squared, that's the denominator, f over g. G times f prime minus, and you alternate. Using the quotient rule and sine x prime, the derivative of sine x cosine, the derivative of cosine is minus sine. Now you can see I'm using what we agreed on. And now we have it. Derivative of cosine is minus sine. Minus sign times minus sign is minus, which is plus sine square, and I have cosine square. That's a famous identity, which we know. That's going to give me 1. 1 over cosine x squared. Notice that the square is written outside. That's one of the ways we prefer. If you want it inside, make sure that it's on top of the letter S and not the letter X, because some students, for some reason, they write cosine x squared without parentheses. It's kind of like, it looks like the angle is being squared. So no, either this way or this way. But we know that 1 over cosine is secant, so this actually is secant square. All right, let me give you a short, quick reference of some rules that you need to be familiar with from now on. Here's a table. Derivative of sine is cosine. Derivative of tan is secant square. Derivative of secant is secant tan. Going the other way around, derivative of cosine is minus sine. See that? This has minuses. Derivative of cotan, instead of tan, cotan will give you minus cosecant square. Instead of secant, we're going to go cosecant. Derivative of cosecant is minus cosecant cotan. Kind of hard to memorize them, but as you go with practice, they become handy. So usually students don't think twice when they say, like, what's the derivative of sine? It's cosine. What's the derivative of cosine? Minus sine, and so on. So the more that you use them, the more that they become like handy, or like 1 plus 1 equals 2. Now the first two are famous, and they are so clear and important to understand from different angles. So I'm going to show you that with graphs. Here we go. Let's look at this guy right here. Derivative of sine is cosine. Then we'll visit this guy here. This is sine x from 0 to 2 pi. If I try to graph the tangents, the tangent right here is horizontal. The tangent right here is horizontal. So if I'm trying from f of x to graph f prime of x, f prime here is 0. F prime here is 0. Now you see the lines. I'm trying to align them and show you that I'm looking at this graph as maybe 4 pieces. 1 here, 1 here, 1 here, 1 here. It's like 4 quadrants, but for me, I'm going to look at them as 4 pieces. On this piece, your tangents are like this. Your slopes are positives. So your first derivative is above the x-axis. Your slope is 0 here. You should be crossing the x-axis. From this point to this point, you are going down. Because you're going down, you should be graphed below the x-axis. Horizontal tangent, crossing the x-axis. Going up, positive slopes, you should be above the x-axis. Derivative of sine is cosine. Derivative of sine is cosine. All right? Let's look at the other way around. This is cosine now. Horizontal tangent, of course, if you see it graphed completely, and you see it graphed, horizontal tangent, horizontal tangent, horizontal tangent. So the derivative of cosine will be crossing the x-axis at where we have horizontal tangents. We're going to cross the x-axis, 0. We're going to cross the x-axis at pi. We're going to cross the x-axis at 2 pi. From this point to this point, you are going up. The slopes are positive. You are graphed as a derivative above the x-axis. From this point to this point, you are going down. Your slopes are negative, so you should be graphed below the x-axis. Just to help you and support those main identities in trig and derivatives of trig functions. Let's take a practical example. Second derivative of secant. How do you apply second derivative? Well, you take the first derivative, then you take the derivative of that again. Let's break this down, a symbol that some students get confused why it's written this way. It's d dx applied twice. Let's apply it first time inside for secant. What's the derivative of secant? It's secant 10. Now to apply the derivative again to what we have now, I'm gonna think about product rule. You know how to apply the product rule. You write secant 10 plus secant 10. Once you find derivative of secant, once you find derivative of tan, and you move on. You can see that? That's product rule. Derivative of secant is secant 10. Derivative of tan is secant square. That will make this one secant cube. That will make this one secant tan square. And we're done. Or you could take one secant out as a common factor, and that should do it. Students sometimes they ask questions like, is this enough or do I have to do this? Either way is fine. In these questions, whatever works, it's totally fine. Unless like in algebra when they say clearly, if the problem says like write your answer in slope-intercept form. Well, that's what the question is asking, so you have to reformat it or write it as slope-intercept form. Just want to give you an idea that this is fine, this is fine. Since this is a lecture with more notes and more ideas and more examples, I'll try as much as I can not to skip and not to make it too short. See the area of the sector of a circle, I could skip it. I could just pretend that everybody knows it. But I felt like taking like another minute or two will show you. Besides, in my description below, I usually break it down. So when you come back to my videos, you can just click on the examples. You could click on whatever you want. You don't have to watch it every single minute. But the video is kind of like complete as a lecture with examples and enough notes. Hopefully that was helpful, and we'll see you next time. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.